until you came to the Big Bang. That's what the second law tells us. The Big Bang must therefore have been a region of very tiny entropy. But what's the evidence that we see a Big Bang? What the evidence is thermal equilibrium. What's thermal equilibrium? You can see it in this picture. It's the biggest region of all. So the entropy went down and down and down and down and down until it reached a maximum. Well, you don't have to be a mathematician to see that that's a bit funny, that argument. So what does it tell you? What this tells you, you see, it tells us there was a big constraint, but it's not to be seen in the nature of the matter and radiation interactions. It's to be seen in the space-time structure. And that you can get a feeling for if you see what happens when gravity is involved. You see, if you just have a gas in a box, then you might tuck it up in one corner, have with some partitions, remove the partitions, the gas spreads out over the box. That's second law consistent. What happens if now these are gravitating bodies, a lot of stars all over the place? What they tend to do is clump. It's sort of the opposite of this. They clump and clump and clump until they reach black holes. So this is low entropy with regard to gravity. It's high entropy with regard to the matter and radiation. What's gravity? That's space-time structure, as we know from Einstein. So what you find is a structure which is very uniform and very high entropy from the matter point of view. It's a mixture of those two. And as time progresses, you could expect clumping and the formation of black holes. Well, we have a very beautiful formula due to Bekenstein and Hawking, which tells you the entropy in a black hole, and this, using this formula, we can deduce that by far the largest contribution to entropy in the present universe is in black holes. It used to be thought that it was in the microwave background. And people should have worried about that, because that would have left them with the contradiction which I just had a minute ago, namely that this initial state seemed to be consistent with thermal equilibrium. However, this is now chicken feed by compared with what could have happened in gravity. So it's the fact that the universe was very uniform which is something that needs explaining, a very remarkable fact. It's not true of the singularities in black holes. That's the other end of the spectrum. So we have to understand why the singularity, where space-time structure goes crazy, is very different in a black hole, and very high entropy in a black hole, and very low entropy in what we see in the Big Bang. Now, I really wanted to make a quick comment here about inflation. I'm afraid there's rather a lot to read here, but the claim is, and I haven't filled in the number here because I had to look it up somewhere and I haven't got it. In the first tiny fraction of a second, the universe was supposed to have expanded exponentially by a factor of, well, the number seems to change no matter what, depending on what you read, but by some huge factor. And this is supposed to explain two of the puzzles of the early universe. One of them, which is why the cosmic microwave background is so uniform over the sky, which indeed it is, to, well, something like 1 part in 10 to the minus 5. 10 to the 5. 2 10 to the minus 5, sorry, that's a misprint. To 1 part in 10 to the 5. To 1 part in 10,000. So it's very, very uniform. And the argument had been, well, how could it know how could that temperature know what that one is? When in standard cosmology, those 2 points have never been in causal contact with each other. There's no way a signal, in the entire history of the universe without inflation, that point could have received a signal from that point to know that it should be the same temperature. So that's one of the arguments that inflation is supposed to resolve, because in inflation, they are in causal contact. By having this expansion, exponential expansion, you find that there is time for this one to get in contact with that one. Details of that I can't go into here. And then there's another thing, is the uniformity, the sort of general uniformity of the universe and the general flatness of the universe are supposed to explain because inflation stretches everything out and produces it pretty well flat and uniform. Both those arguments, it seems to me, are quite wrong. They are accepted these days as being right, but I think they're just wrong. And the main reason they're wrong is that the physics which goes into inflation is time symmetrical. And so you say, okay, suppose you had a universe which wasn't uniform. Well, there's a different argument for this one, but that one says, suppose it wasn't uniform in this sense. Yes. Then, okay, it might not have been uniform. If you need inflation to explain why it was uniform, then obviously it could have been ununiform. But then, suppose you had a universe where you turn time around and it's being ununiform. It has to do something. And whatever it does, you just turn the time around again and reverse that as the initial state. And inflation can't touch that one because it would be a geometry which is so different from the standard models of cosmology that inflation just doesn't work. So there is no reason. Inflation certainly is not this reason. It does not explain this because if the temperature over there was made equal to the temperature over there because at one time they were in causal contact and they thermalize, you see if you have a hot body and a cold body, you bring them together, they become equal temperatures. That's the action of the second law. And that's telling you that the entropy is going up in that process. The thermalization process is always raising the entropy. So that means that after thermalization, the entropy was higher than before it. Therefore, it was even more special before thermalization. So you have a harder job explaining why the entropy was so low.